Let's go ahead and hit record and move into share screen. Full screen. Share screen. Let's get the PowerPoint pulled up. Okay, welcome to Chapter 20. Chapter 20, we're going to have a continuation of information that we started in Chapter 19, which is fuel systems. First illustration that's up in the PowerPoint is of a basic layout of a fuel delivery system. So we've got a tank, float, fuel pump, pressure line, filter, injectors, fuel pressure regulator, and return line. So as you guys read through the chapter, fuel systems can come in a few different formats. They can lay them out a few different ways. In the past, we used to use this return style system that you see on the screen. This was very common. Manufacturers have gone more to the returnless systems, especially with the pulse width modulated fuel pumps. So as we are controlling the fuel pump via pulse width modulation, and we don't have a regulator in the system, as you see right here, we don't really need to have a return line. We can control that fuel pressure at the tank, and all of the fuel that is sent down the line is, on the pressure line, all that fuel that comes down this line is already set at the correct pressure, and it's also set for the correct volume based on the engine load. And so we can eliminate just a redundant fuel line. That does a few things. That's good for overall cost of the manufacturing process of the vehicle, but it's also good for like safety, because we have one less fuel line that can rupture in an accident. The way we go about diagnosing it's fairly simple. It's basically the same. There's not a whole lot different as far as checking a returnless fuel line or one that has the return like this. While I have this illustration up, I'm going to continue on a little bit and talk about some of the other systems you might see if you're working on like older vehicles. And what I mean by older vehicles, it's not necessarily like your Model A or Model T, but some of us might be working in shops where we have maybe like the occasional farm truck that rolls in, an old grain truck that's carbureted. Maybe it's 1960s, 70s, maybe even 1980s. If it's carbureted, it might not have an electric fuel pump. It might actually have a mechanical fuel pump. And so mechanical fuel pumps operate off the engine. And so the engine has like a push rod that's kind of like a push rod you'd see on a valve train. It's kind of like a push rod you see on a valve train, but it comes out maybe the side of the block. And that push rod operates off the cam, and it pushes on a diaphragm, a little tiny mechanical pump. And what you would see in a situation like this is you'd see like the pump would not be back in the tank. You'd just see like maybe the sock filter screen and a pickup screen, and you'd see that run all the way up to the engine block, and the pump would be somewhere up by the engine. And then from the engine, it would pump, your few PSI, 5 PSI or so of fuel up to the carburetor. I wanted to talk about that because there are some situations where the fuel systems aren't going to look anything like what's even in the textbook if you get one of those one-off old school vehicles. And, those fuel pumps on those older vehicles like that, those mechanical style, they can be replaced with electric inline pumps. So keep that in mind if you have an older vehicle and you want to put a more reliable fuel pump on it. Because those diaphragm mechanical pumps it's not that they failed like often, but they have a diaphragm inside of them that would rip, and if that happened, you'd lose all your fuel pressure. So anyway, that's just another system that's out there I want to discuss. Move on to actual fuel injection components. So carburation is where everything started. We've already talked about carburation, the Venturi effect. Carburetors lived in vehicles for 80 some odd years, right? And so the first fuel injection systems that came into play were of like the port fuel style. No, excuse me, no, the central fuel style. So what's up here on my screen is a throttle body unit. And if you look closely, you can see that there's two fuel injectors on this throttle body setup. So this entire component that sits up here on the screen, sits up here on the intake manifold. This entire component is the throttle body assembly. It may be called throttle body. That's more of like a General Motors terminology. Um, some manufacturers call it like central port fuel injection, something like that. But this whole throttle body assembly bolts onto the intake manifold. And on that, we have all the electrical components that are related to the fuel injection. And so you can see a throttle position sensor. See a throttle position sensor that is attached directly to that throttle body. And we also see an IAC. And what IAC stands for is idle air control. So we have to consider fuel injection is electronically controlled delivery of fuel. And so idle speed needs to be a part of that system so the computer can automatically bump up the engine RPM when idle load increases. And so we're going to talk about idle speed control in a later point in this chapter. We're going to come back to it. There's an illustration that I'm going to show you guys here on the screen. But for now, let's just focus on the fuel injection themselves. So these throttle body or central fuel injection systems, they had fuel injectors that literally sat on the top in the airstream, like an airflow stream underneath the air filter, and they would pulse width on and off based on fuel load or fuel demand by that engine. So in the past, like right there, that component, this central fuel injection throttle body component, that was the carburetor. That's where the carburetor sat. So it was an easy transition for manufacturers to switch over to this throttle body unit because they really utilize the same technology from that point down. So like the intake manifold itself didn't change. So the intake manifold is what's in black underneath that throttle body. The intake manifold stayed pretty much the same. There wasn't a whole lot of need to change any of the other technology. And so that made this more affordable for manufacturers because they didn't have to redesign the entire engine. They didn't have to redesign the entire intake manifold. They simply removed the carburetor and bolted this throttle body unit on top and in place of the carburetor. And so something else that's important to pay attention to here is notice where the throttle plate is. You might not be able to see it very well, but if you look closely, you can see these round ports. So there's a round port here, and then there's another round port over here. Right in the lower portion of that port is the butterfly flap, like your throttle plate. So we could also look at the TPS sensor, and if you remember back in class when we passed some of these components around, the throttle position sensor bolts to the axle shaft. So the shaft that runs through the center point of that throttle plate. So as that throttle plate flaps open, it goes like this. I should maybe go like this, and then like that, right? So on the center point, a TPS sensor is shafted into that throttle plate. So that's the axis point. So pay attention here. Where is manifold vacuum? Think about that for a sec. And there's a reason why I'm talking about this. There is significance to this design and what comes after this. That fuel injector is not in manifold vacuum. It's not experiencing manifold vacuum. So it's literally spraying fuel onto the throttle plate. and then the air is pulled via vacuum past that throttle plate, drawing the fuel in with the air down to the individual cylinders that are open, the valves that are opened up. So think about atomization for a second. How well is that fuel going to atomize? It's able to, it's sprayed not really under vacuum. It's just spraying fuel like a like a bottle spraying fuel. It's spraying liquid fuel under maybe 10, 15 psi pressure. So it's not even very like strong spray pattern. There's no jet on this. This is literally just dribbling fuel onto a partially closed throttle plate, where then it has to roll around the throttle plate and be sucked into the intake manifold. That fuel, one of the drawbacks to this style of fuel injection and compared to what we have available today, fuel did not atomize very well. Fuel didn't atomize very well with carburation either. It atomizes probably about the same between throttle body and carburation. But you have to think back, when was this style of technology introduced? We're going back to like the late 80s is when we started seeing throttle body central fuel injection uh, put on vehicles. And so going from carburation to central fuel injection, if you put yourself back in 1985, for example, and this is like lightning, lightning. This is like just a major improvement in technology in comparison to what they had. We didn't have direct fuel injection or port fuel injection to compare this to. This is like having a computer or having a book. So like being able to look up information on a very primitive, internet platform like dial-up internet, being able to load a screen that took 30 seconds to refresh versus having to drive to the library and check out a book. So there's a major difference in technology. It was a major improvement in technology. Today we could look back on it and kind of laugh because it really isn't that good. But compared to what was available at the time, it is a major improvement. And so manufacturers were trying to get control of the fuel economy and the emissions on vehicles. And so in order to do that, we had to put some sort of electronic computer control system on these engines. And this was the solution. This was the basic layout of how most manufacturers made that transition from carburation to computer controls. But now think about what else is going on here. There's a few components that a carburetor didn't have that were a major improvement in technology. For example, a throttle position sensor. The throttle position sensor is direct feedback to the computer for where the throttle plate is, so the computer can determine how much air is flowing in, for example. Carburetors had no way to determine how much air was flowing in. It just sprayed fuel, right? And so when a driver was accelerating and now deaccelerating, coming off of a highway, the computer could sense the throttle plate closing and it could deactivate the fuel injectors so they'd stop spraying fuel. That right there is a huge improvement. Someone's knocking on a door. I'm in a meeting. Go away. So carburetors didn't have the ability to shut off fuel as you deaccelerated. All they did was simply just, as the engine's still pumping air, it still sprayed fuel. And so how much fuel do we really want to have while trying to slow down? Don't want to have any fuel. There's no reason to have fuel because you're not trying to build horsepower, you're trying to stop. And so just that little simple addition of a throttle position sensor allowed manufacturers to improve fuel economy by a minor amount, but still, it was an improvement. Let's take a look at the next screen here. Port fuel injection. Port fuel injection came out shortly after throttle body injection came out. There was maybe 5 years, 10 years, a window that was relatively short where manufacturers made the switch. Some manufacturers didn't even use central fuel injection. They just simply went straight to port fuel injection. Port fuel injection placed an individual fuel injector behind every intake manifold valve, intake valve. So we take a step back, look at the location of this injector. We have one or two injectors that have to spray fuel to the entire engine. So if this is a V8, the front two cylinders, the back two cylinders, the middle four cylinders, they're all getting their fuel from the same fuel injectors. Fast forward to port fuel, we now have an injector that's placed behind an intake valve per cylinder. So now we have an injector located right at the point where the fuel is actually needed. So think about that for a second. What's going to happen in this previous illustration? We have an intake manifold. I'm not sure if the book, in the chapter, there isn't really a great image of an intake manifold, but you've all seen intake manifolds. The intake manifold, if we're spraying fuel at the beginning of where air enters, the air has to travel a long distance, and the cylinders at the front and the cylinders at the back are going to get a different mixture of atomized fuel versus the cylinders that are directly below these injectors. So we'll actually, in this setup here, we'll end up with a situation where we have varying air fuel ratios that are delivered to the front cylinders and the back cylinders versus the middle cylinders. The fuel, as it tumbles through the intake manifold, it has a chance to pool up in the further cylinders where it actually formed like droplets again as it cools back down. It's just a mess. And so port fuel injection puts that fuel injector right at the final point of right before we actually need the fuel. We have an intake valve, we have air flowing in, and as that intake valve is opening, we spray the fuel. And so by doing that, we allow for the maximum atomization of fuel delivery. So as that fuel is being sprayed, it has turbulent airflow that's also working with it, pulling that fuel in, allowing that fuel to tumble around and atomize. So that's your typical port fuel. And we call the most modern port fuel, we call it sequential port fuel. There's a few different kinds of port fuel systems that are out there. In the early days, the technology wasn't so good that we could literally fire those injectors on a firing order. And so they used a system called gang fire or batch fire. And so if you had a V8, for example, they would spray the even cylinders and then the odd cylinders, then the even cylinders and then the odd cylinders. Well, sometimes you'd have a valve that was open. Sometimes it would spray against a closed valve. The engine was running, at 1,000 or 2,000 RPM. The fuel didn't really have a chance to cool up on the backside of the valve, even though technically it did. But in the early days, we didn't fire sequentially. If you're working on a vehicle from like the mid 90s to current that has port fuel injection, it's going to be sequentially firing that fuel. And what that sequential part is referencing is it's just a firing order. It's no different than if you look at like how your ignition fires, or if you look up the firing order of an engine, as cylinder number 1 fires, maybe cylinder number 2 is on an intake stroke, maybe cylinder number 3 is on an exhaust stroke, etc. And so we're sequentially firing that fuel in time with the intake valve, so that way we have that rush of air moving at the same time we fire that injector, so the fuel has the best chance to atomize and has the least opportunity to sit on the backside of the valve and cool up. Because that was another issue with like central fuel injection and carburation. We're just spraying fuel on the top side of the intake manifold, and that entire air charge has fuel in it, but it doesn't have fuel equal distribution. It doesn't have equal atomization of fuel. It doesn't have uh, equal air fuel ratio. It's enough. It's close enough to where the engine can run, but it's not good enough for efficiency factors. So port fuel injection did a great job. Port fuel injection actually lived probably up to this point of, I should say, sequential port fuel injection. Out of everything we've talked about today, minus carburetors, out of all these advanced fuel injection systems, it lived the longest. It's only now being phased out. And since maybe 2010, that's when you started seeing direct fuel injection really come into play. But still to this day, there are manufacturers that are selling brand new cars with sequential port fuel injection. It's going to be around for a little while yet. If I had to take a guess, I'd say probably in the next maybe 5 years, you'll see it just go away entirely. But all right, so I think there was something else I wanted to discuss. Oh yeah, one more thing. I brought up previously in the last diagram the location of the injector versus the throttle plate. So in this image, we have an injector that is experiencing manifold vacuum pull. In this image, those injectors are not experiencing manifold vacuum pull. So this is just a theory point that I want to discuss. This is part of the computer programming and considerations that are made by manufacturers and manifold vacuum, and something that you need to consider when maybe diagnosing some weird complex issue. The engine is assisting the fuel flow out of your port fuel injector. That might confuse you a little bit, but if you think about it, if I have manifold vacuum, this entire intake manifold is under vacuum. At idle, with the throttle plate closed, 17 to 21 inch-pounds of vacuum. So I literally have a vacuum effect on the fuel injector. On the other side, so that's the pintle side, right? The injector nozzle side. On the other side of the fuel injector, I have a fuel pump that's building 30, 40, 50, 60 psi, whatever it is, pushing fuel. So on one side of the injector, I have manifold vacuum pulling the fuel out of the injector, and on the other side, I have fuel pressure from a pump pushing. Why is that important? It's theory, right? Just so you can fully understand the full effect of the two effects on a fuel injector. Manifold vacuum has a play on fuel delivery. And so the integrity of an engine, its mechanical integrity, will actually affect the amount of fuel that is delivered to a cylinder. So keep that in mind if you're ever diagnosing some misfire issue or some fuel trim issue, and you got an engine that's running kind of rough, and in the back of your mind, consider the fact that the fuel injector, if it's designed to spray 20 pounds of fuel per hour, that's typically how we rate injectors, is like how many cc's and volume per hour per minute. There's some sort of weight of fuel over time. There's a maximum amount of fuel that an injector can deliver, and it's also based off of, that number is based off of pressure. And in addition to the pressure, the vacuum is also a factor in that flow rate for that fuel injector. If you get into like high performance building, those of you that want to build race cars or something, you get into tuning software, this becomes a very big deal. Because if you change out fuel injectors, you have to tell the computer what it has for a fuel injector. And if you change like manifold vacuum with a camshaft, or you change like to an aftermarket fuel pump that's at a different pressure, things get crazy in a hurry. But for your average, just passenger truck that's going to come into your shop, it's not going to be as big of an issue, but just keep it in the back of your mind. Manifold vacuum has an effect on fuel delivery because it helps pull the fuel out of the injector. All right, so fuel pressure regulators. We talked about fuel pressure regulators last week in chapter 19. We talked a little bit about like where they're located and a little bit about the purpose and function. I want to get into that a little bit more in this chapter. So what I was just talking about is kind of like the introduction to this. So when I was talking about like the injector and the flow rate, the computer can only deliver fuel accurately if it has correct fuel pressure. And so if we think about like a computer trying to add fuel or trying to subtract fuel, so plus on fuel trims, minus on fuel trims, that's all based off of like that pulse width that it's going to command. It's all based off of these factors, these like norms that it's assuming are correct. And so try to explain that a little bit better. If a computer is going to spray 2 milliseconds worth of on time, so it's going to inject that fuel, turn on that injector for 2 milliseconds, it's assuming that fuel pressure is correct. It doesn't know that fuel pressure is high or low. On your more advanced fuel injection systems that are pulse width modulated, where we are supplying fuel pressure on demand and fuel volume on demand by cranking the speed up or down on the pump, there typically will be a rail pressure sensor for feedback, so the computer technically knows what the fuel pressure is. That's assuming that the fuel pressure gauge is correct, like the sensor on the rail is delivering correct information, which is a whole world of other problems and other discussions if that goes bad that we'll talk about. But the computer, we go back to like take the pulse width modulated systems out of the equation for the moment. If the computer is going to control pulse width on injectors in order to control the fuel delivery, then the fuel pressure has to be correct. So however the manufacturer programmed that computer, they had a baseline of fuel pressure and volume to go along with that pulse width of the injectors. So the fuel pressure regulator's job is to maintain that set fuel pressure. And that set fuel pressure can fluctuate. It can go up and it can go down based on engine load. Typically with heavier load, wider, your throttle plate's wider, trying to accelerate, you'll see fuel pressure climb by a few PSI. The fuel pressure regulator's job is to maintain that consistent fuel pressure at all times. The pump can typically push out multiple times the pressure. So if the pressure regulator is set at 50 psi, the pump may be able to put out 100, 150 psi. It's limited by the fuel pressure regulator. So the pump will feed the pressure regulator. The pressure regulator has a set spring and or electronic. There are electronic pressure regulators out there. And what it'll do is dump off everything beyond that set pressure. So if 50 psi is what's needed for that engine to run, so the manufacturers designed the entire computer system to deliver fuel based on 50 psi, that regulator will hold the fuel rail pressure at 50 psi. Anything above that will be dumped off back to the tank and not used. It'll literally bypass the fuel rail entirely. And if it doesn't so let me restate that. It depends on where the regulator is located. If the regulator is located in the tank on a returnless system, it'll bypass internally right there in the tank. If the pressure regulator is located up on the fuel rail, it'll hold fuel pressure in the rail at that 50 psi, and then it'll dump off everything else on a return line back to the tank. There's a variety of different ways manufacturers do this, but if they incorporate a fuel pressure regulator, the regulator's job is going to be the same. It's to maintain the fuel pressure at all times. And so fuel pressure regulators can be, if you're just your set spring style, where they just hold one set pressure all the time. They can be vacuum style, where they allow for a little bit of increase in pressure based on manifold load. And they can also be electronic. You saw electronic fuel pressure regulators incorporated into vehicles more in the last like 10 years. You didn't see electronic anything on fuel pressure regulators until probably the late 2000s, 2010-ish, around there. There are manufacturers today that are still using just a spring style and have no electronics at all. So it's important when diagnosing fuel system issues to always go back to service information. Sound like a broken record here, but you always have to go back to service information to figure out what exactly it is you're working on, what's in the system. Excuse me, working on a cold or something here. Hope it's not the coronavirus. I don't think so. I'm at week 1 of whatever this is, but I'm feeling pretty good at this point. So, all right, let's take a look at the rail. We have a typical fuel rail here in front of us. Anybody take a guess at how many cylinders we have? You said 6, you're correct. So, we have 6 fuel injectors. We have a fuel pressure rail. We have a fuel pressure regulator on that rail. And we have a pulse dampener. So this is the point where we'll talk about pulse dampeners and some of the ways manufacturers go about combating fuel pulsing in the rail. So the chapter talks about this just a little bit. Okay, first, what is the fuel pulsing? So if you think about how a fuel pump works, it's not just on, it's on, off, on, off, on, off, on, off. It operates on a frequency, hertz, right? So that's true even with your simple on-off fuel pumps. So your pulse width modulated pumps on your later vehicles, it's even more of a problem. But on your earlier stuff, if it had an electric fuel pump or a mechanical fuel pump, didn't matter. Both of these styles, they don't operate just on, they operate on off so quickly that they seem to just be on, but they're actually pulsing fuel in waves. So your fuel is, as your pump is increasing, so it's moving, the armature is rotating, it's turning on and then off, then on, then off, then on, then off. And what happens is you have a burst of fuel, and then you have a slowdown of fuel. And then you have a burst of fuel and a slowdown of fuel. That's from the pump up to the rail. But then you have another issue. You have injectors on the rail that are opening and closing. And so you have this constant increase and decrease of fuel pressure and flow and volume happening inside the injector. And what can happen is you can end up with an inconsistent fuel flow in the rail. So I just talked about how the manufacturers need to have everything they design for pulse width on an injector is based off of like a guarantee that there will be X amount of fuel available at that injector at all times. So fuel will hammer. Some people might have this in their house. You may hear like a hammering noise in your house with your plumbing. Like you're open a faucet and you shut a faucet and you hear this like hammering noise. That's the same idea what's happening in the fuel rail. So if you have that increase and decrease in fuel pressure and volume because you're opening and closing the injectors and you have a fuel pump that's on, off, on, off, on, off, you don't have a consistent fuel delivery to that injector. When that injector goes to open, it might not get the exact same amount of fuel into it every single time. And so that decreases the the efficiency of the entire system. The predictability kind of goes out the window. And so, in order to combat that hammering effect on fuel delivery, what manufacturers have incorporated are dampening devices, kind of like shock absorbers. And so, what they'll actually do, this pulse dampener is just one illustration, but what they'll actually do, the theory is pretty much the same on all of them. They'll act as a shock absorber so they can actually push back to like a middle position of travel, and as fuel kind of like goes down in pressure, they're able to add a little pressure, and then as fuel is um, too great, as it hammers, it'll actually absorb that impact, and so it literally acts just like a shock absorber on your suspension on your vehicle. It dampens those violent shocks and kind of smooths everything out. Doesn't make it perfect, but it eliminates almost all of the hammering by having that pulse dampener on your fuel rail. And so you may see a weird looking, round piston or round, something on the fuel rail, and you're not quite sure what it is. If it doesn't have like a secondary fuel line leaving it, that's probably what it is. It's probably a dampening device of some kind. They look very similar on a lot of vehicles to just a fuel pressure regulator. So don't confuse it with the fuel pressure regulator. It's kind of hard to confuse them with the regulator, but they look similar. And so if you just see this round object. Now, another way manufacturers will assist in dampening is by the shape of the rail itself. And so in the textbook, I know it's in there, I saw it somewhere, on page 264, figure 20-15, you see like this rectangle looking fuel rail. That's one of the ways General Motors try to combat that dampening, that hammering, is by changing the shape. It's something to do with the shape. I don't know. I'm not an engineer. I don't know exactly how the fluid dynamics work there, but they changed the shape to more of a rectangle, and somehow that also assists in fixing that hammering effect. So, all right, let's take a look at a cross section of a typical port fuel injector assembly. If we look on the right side, we see a screen. This is the inlet. The internal point is the coil winding, the actual, it's not the mechanical parts, but it's the electronic parts of the injector. And all the way at the very end, we have the injection nozzle, like the valve. Sometimes this is referred to as a pintle. This is the portion that actually plunges in and out, up and down. And so from right to left, let's talk about this. In previous chapters, I discussed like the final filters that are always in the fuel system. So you typically have a sock filter in the tank, and then you have a like inline filter, something, it could be in the tank still on a lot of these newer vehicles, but you have a sock filter that just picks up the minor debris before fuel enters the pump, and then from the pump we go to a more fine filter in micron, and then from there we deliver all the way up to the fuel rail, and there's always a final filter. It can be in the injector, it could also be maybe in a fuel pressure regulator, but every injector I've ever taken apart has always had a final filter in it. And if we look right here, this little meshed area, that's where that finer filter will be, the final filter. Sometimes you'll hear them referred to as like a basket. I've seen in terminology, they'll talk about like the fuel injector basket. That's the final screen. It's a very, very, very fine filter. In theory, you should be able to drive that vehicle for hundreds of thousands of miles and never plug up those screens. But what happens is people don't change their inline filters, and for whatever reason, maybe the inline filter degrades because a lot of times they're just a paper element, and they allow bigger junk to pass through. And so that bigger junk will end up landing in these baskets and clog individual injectors. Which reminds me, one more thing here. Think about the flow of the fuel in. On your returnless systems, keep this in mind. If you have a situation where the vehicle experiences junk moving through the fuel rail because the filter didn't pick up on it or the filter degraded in line, if it's a returnless system, typically the last injector in the line is the one that'll collect all of that junk. So you think about the way the fuel flows, it's going to move through the rail, and at the very end, on a returnless, the very end of the rail is the end of the line. Fuel can only go through that last injector. And so what will happen is all that junk will get pushed all the way through that fuel rail, and it will end up depositing in the basket of the final injector. So if you end up with a misfire situation you're trying to diagnose and you can't figure it out, just because the fuel injector is pulsing does not mean the fuel injector is delivering fuel. It can be clogged. Mechanically, it can be working just fine. You could have fuel pressure, you could have fuel flow at the rail, but if you have a basket that's clogged on one of these injectors, you'll have an injector that appears to be working fine, but is not actually delivering any fuel. So, moving on. All injectors have some sort of electrical connector. Obviously, it goes without saying. They're electronic devices. They have to have a connector. They're typically 2-wire. So, what I mean by that is they have a positive and they have a negative. Because internally, there's a coil. And so, this coil operates on the magnetic theory. As I energize the magnetic field with my negative and positive wire, I create an induction of magnetism, and I pull a plunger. It operates just like a relay. If you've opened up relays and you've looked at how relays work, I energize a relay, I create a magnet, and I pull a switch. Door locks, whatever. The injector, as it's energized, will pull on a plunger. Okay, so internally, this plunger will slide to the back. Fuel internally is able to pass then through the injector and spray out on the other side. So kind of think about a fuel injector as a door. You have fuel on one side of the door and you have nothing on the other side. You have a cylinder. The injector, as it's turned on, is going to momentarily open the door and allow fuel to flow. As the injector is turned off, there's a spring that'll hammer that injector back shut. Think about how quickly this injector has to move. Milliseconds. They're very fast reacting electronic components. They have to be able to open and close in milliseconds. Think about an engine that is running at 3,000 RPM down the interstate. That injector could be opening thousands of times per minute, nonstop, cycling back and forth. So not only do they have to be able to move very quickly, they have to be able to do it over and over and over and live a long life. So fuel flow is very important to the injector's life. The quality of the life of the injector depends on the quality of the fuel. The fuel is the lubrication for most fuel, not for most, for all fuel injectors. Fuel literally is the lubrication for all the internal components. Fuel is also the cooling component. So think about this. We have an electronic coil that's using electricity, it's going to get hot. It's going to pick up heat. The fuel moving through the injector is what dissipates the heat. It's like the radiator effect on the fuel injector. So operating injectors at max duty cycle. So that's another term that we talk about with fuel injectors is duty cycle. Pulse width on off is in milliseconds. Duty cycle is a percentage of on time versus off time. So all fuel injectors have a maximum duty cycle, roughly 85-90% on time. So meaning that out of a given set of time, if you set 100 seconds, they can only be on for 85 of those seconds. They have to shut. Otherwise, they'll overheat. They cannot stay on 100% of the time. Now, the scenario where that would happen would, I mean, that's just insanity. No manufacturer has a vehicle in production that, with a factory setup, tune, everything, none of them run beyond that 85%. Where you see this happening most commonly is in your, again, your aftermarket guys doing like horsepower builds and race car stuff. That's when it's time to upgrade your fuel injectors, when your fuel injector can no longer maintain that appropriate duty cycle time. So I was trying to think, is there anything else on this slide? I think that's about it. So let's move on to the next one. Illustration of port fuel spraying in. There's debates out on this. When does the fuel spray versus the intake? I'm not going to get into it. Every manufacturer is a little bit different. What I'm talking about is there's arguments on the internet. You can go read this stuff. Does the fuel spray at the backside of the closed valve, or does this fuel spray as the valve is moving off of its seat? When does the fuel? Doesn't matter. For all theoretical purposes, the port fuel injector sprays at the same time the intake valve opens. The only time it'll spray on the backside of a closed valve is on your very, very old school batch fire, gang fire injectors. Everything that's sequential, that fuel injector is spraying at the exact same time the intake valve is opening. If it's millisecond before, millisecond after, it doesn't matter. All right, let's talk about long intake runners versus short intake runners. Um, Manufacturers have a few different ways they lay out intake manifolds, and we've talked about this a little bit in the class in the past. So intake manifolds can come in short runner or long runner. You typically see your long runner intake manifold designs on your pickup trucks. You see your short runners on your cars, and then you also see a hybrid blend between both. Some manufacturers will literally use a flap on the inside of a manifold in order to switch between a long port and a short port. The long runners, what they do is they allow for the density of the air to build up against the valve and act as like a little bit of a micro force induction effect. So as that airflow is moving and the intake valve shuts, that air is still moving. An object in motion likes to stay in motion, and so you get a compression effect on the backside of the valve. So as that valve opens up again, you get a little burst of extra air into that cylinder. The problem with the long runner is the faster you move the air, the more violent the airflow becomes, the more turbulent the airflow becomes, and the more of a restriction the airflow actually makes because of itself. As the airflow is increasing in volume and speed, I shouldn't say volume, as it's increasing in velocity, it starts to tumble. The faster it goes, the more it tumbles. The more it tumbles, the more it starts to restrict the overall port size. And so you typically see pickup trucks with long runners because you can gain a little bit of low end power and you don't run your truck at 7,000, 6,000 RPMs ever. But when you get into like more of your cars, your passenger cars, we tend to have a short runner because we need that power band at the higher RPM. I don't know. Manufacturers can do this several different ways. They can incorporate whatever they want to incorporate, I guess. But I just want to touch base on that a little bit because it's in the chapter, and I know we've talked about it in the past, but just a little review. So, typical port fuel injection system showing the vacuum controlled regulator. So in this diagram, we can see that regulator. We got the pump, we got the line, we got the filter, we got the rail, all the injectors. The regulator sits at the end of the rail. The vacuum diaphragm sits up here on the top, the vacuum supply. Everything else is dumped back to the tank. And last chapter, when I discussed the importance of paying attention to like that diaphragm ripping, you can see here nicely in the illustration how the there's my cursor, where that little flap sits, that little diaphragm rubber flap, and if it were to rip on the other side of that, you have your vacuum. Another illustration of how the actual vacuum regulator works. As vacuum is applied, we're pulling up on a seat. So the spring right here, I think I can actually draw on this. Let me see where the, there it is. So get better at this with time, guys. So as vacuum is moving up, why is it baby blue? Come on, this would be a better color than this. Format, color, there you go, red. All right, so as manifold vacuum is pulling up on this scenario would be like throttle plate closed, right? So at idle, pay attention to the PSI. At idle speeds or low load, throttle plates closed, partially opened. We don't have a demand for lots of horsepower. Our fuel pressure is going to be set a little bit lower. If you look over here, no vacuum applied. This is a case where the throttle plate is wide open. Look what happens to fuel pressure. So the spring is pulled back with the vacuum, which actually allows more fuel to be dumped off. As that spring is able to push down, it blocks off some of that return to the tank. And so if I block off and pinch off a little bit, make a restriction on the return side, I'll cause the actual fuel rail pressure to increase. Make sense? How do I move on now? Great. Hit X. Okay. Move. Next. There. I need to get rid of my clear. Clear all drawings. There we go. Okay. Little side view cut into a regulator. This is a vacuum regulator. Here's one of those screens and filters I talked about. If you didn't see this picture, you probably would never know that there can be a filter inside of a fuel pressure regulator. It's not uncommon to see that filter, that little screen, located on the other side. So as you pop that regulator off of a fuel rail, you might see a little screen. Every single regulator I've ever replaced, if the screen is internal, you don't even see it. But if it's external, in the regulator, the box, when you buy a new regulator, it'll be in the box. So if you pull that regulator off the fuel rail, don't forget to always look into the fuel rail and see if there's a screen in there. If there's a screen in your box, or sometimes what they'll do is they'll actually push the screen on the new regulator. And so what'll happen is you'll pull off the old regulator and that old screen can get stuck in the rail. And then you have a new regulator with a screen on it. And I'm not talking about the one that's internal here. I'm talking off to the side. There could be one over, on the service side. It's kind of like if you change oil, you got a filter, and the oil filter O-ring stays on the engine. The new one has a filter. On the new filter, it has an O-ring as well. So you always have to double check that the old O-ring is removed. In this case, always double check that the old screen is out of the rail. Otherwise, you're not going to even be able to get the regulator on. That's what's going to happen. You're going to sit there and you're going to fight for 10 minutes until you finally look inside the rail and you see the old screen filter, and you can't, you'll have to pull that out before you can move on. So anyway, I don't know where I'm going with that, but too far. Okay. So fuel pressure sensors, fuel temperature sensors are often constructed together in one assembly to help give the PCM needed data to control the fuel pump and fuel pump speed. So now we're on to um, computer control fuel pumps, pulse width modulation, controlling the speed of the pump in order to control the pressure and the volume of the pump. So if you look at this illustration here, you'll notice that this is a returnless system. There is no return line in this fuel diagram. And so we have a module that is controlling the fuel pump's speed in order to control the pressure and volume of the fuel that's coming into the rail. And so this is a very typical illustration, very basic example. Manufacturers can lay this stuff out a little bit differently, but generally this is how it's going to look. You have a PCM, so that's powertrain control module. So the powertrain control module is the engine management, powertrain management. It is talking to a fuel pump module, which is over here. So let me get this, go back. Let me get my illustrations pulled back. Annotations, whatever. Let's get draw. Let's do this. Okay, so your PCM is talking to your fuel pump control module on some sort of data line. It's not uncommon to see the link between these two on a CAN bus line. So think about CAN bus network. This is a perfect example of why manufacturers want to have a CAN bus network on a car, because they're going to have a high-speed data line running from the front of the car to the back of the car, typically the fuel pumps in the rear. I don't have to have all these redundant sensors feeding that fuel pump module, et cetera. It just makes things easier. So this fuel pump module can be in the tank. It can literally be like a part of the fuel pump. Typically, they're going to be located on the outside of the fuel tank, somewhere mounted near the fuel tank, and they're going to have, so you're going to have a fuel pump module that's talking to a PCM, but that fuel pump module also has a power wire and a ground wire that it's going to feed down to the fuel pump itself in order to control the fuel pump. So the PCM talks to the fuel pump speed control module. That control module is what's actually pulse width controlling the fuel pump. The fuel pump sprays fuel out down the rail, and then we have this guy right here, the fuel rail sensor. So that's the temperature sensor. Here's the pressure sensor. Those two sensors are feedback for how the fuel pump is doing. So if the PCM says, hey, I need more fuel, it's going to communicate that information to the speed module for the fuel pump. The speed module for the fuel pump is going to increase the pulse width on-off time of that pump. It's going to spin it faster, which in theory should give more pressure and more volume. The fuel pressure sensor on the rail is going to say, yep, I got 60 psi. You asked for 60, I got 60. And it's going to communicate that back to the PCM. And this is all happening very quickly. In the next nanosecond, the PCM may say, okay, the guy just slammed the throttle plate shut. We need to shut this thing down a little bit. And so it tells the fuel pump module, I don't want 60 psi anymore. I want 50 psi. And so the pump slows down. The fuel pressure sensor sees the 50 psi and reports back to the computer, hey, we got 50 psi here. Everything's working just fine. The problem in these systems is the diagnostic side. So if you think about what can go wrong, if I had a fuel pressure sensor that was bad and it was giving false information, maybe it's reporting 50 psi all the time, you're going to end up with trouble codes because you're going to have a fuel pump that's going to be trying to increase off of 50, but the feedback is saying that it's not. And so if the fuel pump is increasing to 50, 60, 70 psi, and the rail sensor doesn't actually show that, you're going to have trouble codes that's set. This is a conversation more for like advanced diagnostic stuff, but if you're working on a vehicle that is experiencing some sort of drivability issue, and you scan that car and you see trouble codes for like fuel pump speed control module, inadequate fuel pressure, something weird like that. Look up the descriptions on that code. A lot of times, what it's going to point back to is like the fuel pump commanded, or the fuel speed module commanded 70 psi. The fuel pump was only able to put out 50 psi. Well, it's not necessarily the fuel pump. It can be that the fuel pump was unable to put out the set pressure because it's just a worn out pump. But it could also be on the feedback side. So the fuel pressure sensor itself, if it's not reporting accurately, you're going to end up with a very confused electronic control system on this engine. And it'll start pointing fingers at different components. And it isn't necessarily the component that it sets a code for. So if I have a fuel pump module that's saying, hey, pump, turn 70 psi, and it reports back that it's only turning 50 psi, it's probably going to set a code for a fuel pump unable to like maintain pressure. But what if you have a filter that's bad? Right? What if that filter is bad and it's blocking the fuel pump and it can't actually get the fuel to the rail where the sensor is located? It's going to set a code for a pump, but in reality, it can be something other than the pump. And so the diagnostic flowcharts on these are very important. We always pay attention to all the system components before we just start chucking parts on these cars. Because you can also have something else wrong, like a fuel injector that's stuck wide open. I mean, look at this illustration. If I had a fuel injector that was stuck wide open and just spraying fuel, dumping off fuel, there's no way that that fuel pressure sensor is going to be reporting identical command pressures because you're bleeding off pressure as the engine's running. Now, of course, you should be wise enough to also note the other drivability issues in all of these situations. So those drivability issues are going to vary drastically as well, because obviously if we have an injector that's stuck wide open, imagine the black smoke, the misfire, hopefully customer drivability concerns. There's going to be a lot of other things that play into this. So sometimes just the effect, like the actual customer complaint, is what we're using as our most valuable, insight to this. But these are topics for other days with advanced diagnostics. We're definitely going to be talking about this type of stuff more, how to diagnose these systems. But this is just the overview, and hopefully that's a decent explanation there. So let me clear all my drawings and move on, if I can. Okay, so mechanical returnless fuel systems. This is another way manufacturers will set up the returnless systems on fuel injection components. This is more of it's an older design. And so the book talks about electronic returnless, mechanical returnless, and then like on-demand stuff. So this returnless system, if you go and if you want to see an actual picture, I remember this part number because I've used, my Honda actually has this exact style filter. Napa part number 3737. I'm weird, I know. I just memorized that because I bought so many of those filters. But this filter, this mechanical returnless system, the filter itself has a regulator built into it. It's kind of crazy to think about, but the fuel pump leaves. So let me get the. Oh boy. Okay. Let me get animations, whatever they call that, pulled up. So fuel is going to leave the pump, leave the tank, just like a normal return system. But immediately after leaving the pump and the tank, it's going to hit a filter that's located very, very, very close to the tank. So maybe within like a foot or two. It'll be located very close. And the filter then has an inlet and two outlets. So one outlet is to dump fuel back to the tank, the excess pressure. The other outlet is to send fuel down to the rail. It's a bizarre system. It didn't last for very long, but it's a very simple way to set up a returnless system on a vehicle without getting, excuse me, really complex. So the filter itself, every time you change the filter, you're replacing the regulator as well. So that's actually one nice feature about this is if you're changing the filters every 30 or 40,000 miles, you're always replacing that regulator. And they're really not that expensive. You'd think that this would be like $100 part. They're really not. I can't recall offhand how expensive they are, but they're not probably more than 25 bucks. They're not expensive. So that's like a mechanical returnless system. You'll see that on some vehicles. I can't even recall. Like, it's not that common of a system. It's out there, but you're probably not going to run into this very often. Just keep that in mind. This system does exist. Okay, clear all drawings. There we go. Move on. So, on-demand delivery systems use a fuel pressure regulator attached to the fuel pump assembly. So, in the fuel pump itself, so we look at this illustration, we have a fuel pressure spring, a paper filter element, return system. This is all inside of the tank. So your demand delivery systems, this is your, when I talked about how manufacturers are putting the filter in the tank, they're putting regulators in the tank, and you've also got the sending unit for like the fuel level, the pump, the sock screen for the pump. All these components are now being located in the tank. This is an example of that. So this is not a pulse width modulated pump. This is a like mechanical regulator system. Okay, and so the manufacturers are going to set this rail pressure at maybe 50 psi, and so where that rail pressure is actually being regulated is in the fuel pump itself mechanically. So down inside the tank, we have a fuel pump module assembly, $1,000 part. That's all or none, right? So we've got all of these components built into one central fuel pump assembly. And inside the tank, we're going to limit the fuel pressure. And so fuel pressure is going to hit the outlet side, and the entire time is going to be consistent, the exact same pressure. Anything above what the pump makes, anything that the pump makes that's not needed, is just dumped right back into the tank. So it's a fairly straightforward way to do it. You'll run into this. This is a very common system. I've seen this on a lot of vehicles. This was probably more common, definitely more common than this style here with the filter, doing it external. This is kind of like a patch, like having the filter, have the regulator built in. It's kind of like a patch to where like the old inventory could be used up before they switched over to like this new design. There's a picture of that fuel rail I talked about on page 264. Rectangle fuel line. There's your fuel injector, your connector. You can see two wires going into it. Another diagram of a fuel injector, multi-port injector. All right, let's talk about this illustration here. Figure 20-17. Fuel injector spray patterns. Okay, so all fuel injectors have to, they're designed to spray fuel in such a way that it helps atomize fuel. And if you look very closely at some of these pictures in your text, you can actually see from left to right different spray patterns. So if you get on the internet, you can look up this stuff a little bit more, but I'm going to talk about this guy. So look at this one, spraying two little jets sideways. This one's spraying a straight jet. This one's spraying like a whole bunch of droplets. All these are pretty jacked up. Trying to see if any of these look really good. This one kind of looks all right. That one you can see a stream. So when fuel leaves the injector, it has to leave the injector in a mist, a fog. And maybe I'll include I think I've got a couple videos on YouTube saved. I'm actually looking at the fuel flow of these injectors, like bench testing them. And so if the fuel has to leave the injector in a mist, it has to atomize, poof. And if it comes out in a jet, or in droplet form, that's liquid. Fuel cannot burn if it's liquid. It has to be atomized into like a fog, a mist. And so part of the injector's job is to push the fuel out in such a way that it instantaneously atomizes. And we can end up with drivability issues from fuel injectors that become clogged. And so if we go back, I'll go back to the other injector picture, the page before this, I think. Yeah, here. So the pintle itself is where the fuel is leaving the injector. And what will happen over time, the pintle will become carboned up. That's one of the ways that injectors can go bad. So if the injector pintle becomes carboned up, then it's kind of like you're partially blocking the outlet of the injector. So fuel isn't going to run in a mist, it's going to hit that carbon and kind of bounce. And as it does, you're going to get like a collaboration of that fuel, and it's going to turn into like a dribble or a droplet or just a straight liquid form. And that won't burn. And so the computer then has to compensate by increasing the pulse width of that injector to spray even more fuel out in order to satisfy the oxygen sensors, fuel trims, etc. And you'll end up with engines that have a misfire, engines that have poor fuel economy, have elevated overall tailpipe emissions. Okay, and so one of the things that you can do is you can run like a fuel injection cleaning service on car, so you can leave the injectors on the rail and you can run a product like seafoam through the tank, for example. That's an injector cleaner. And so what that'll do is go through the injector and bust up a lot of that carbon and help restore the flow. Uh, in some cases, you'll have to remove the injectors and send them off. You can have an injector that is mechanically working, but not able to spray fuel correctly, which would cause a misfire or poor fuel economy. Oh boy, central port fuel injection systems. This is your spider injector. Page 265. Talk about junk. I hope none of you drive a vehicle with this style injector. You'll understand what I'm talking about if you ever go. There it is. If you ever go service a vehicle. Um, General Motors is the only manufacturer that I'm aware of that use this. There are probably other manufacturers that use this injector style system, but what's going on here is you basically have like a distributor. So in the center of your in the center of this system here, you have like a distributor style, in theory, fuel pump. It's not even a fuel pump, but it rotates, and when let's call this cylinder number one. When cylinder number one needs fuel, it's lined up and it's allowing fuel to spray down this line, and then it allows fuel to spray as it rotates down this one, then this one, and at the very end, you have like a poppet style component there. And so the poppet basically at a certain pressure, it's like a check valve, and it allows the fuel to move past that poppet, and then as the fuel is diminished, the pressure drops in the line, and it moves back. So this illustration here is the aftermarket replacement of the style leading up to it. So there's actual injectors in this one, but in the original style, there were no injectors. They were just like a poppet valve. And so what will happen is those little check balls will break, and so the fuel pressure will just be dumping down that port at all times, and you'll end up with engines that just don't even run. I mean, they'll run so rich that they'll literally hydrolock themselves. One of the only times I've ever seen, and I've seen this a few times, one of the only times I've ever seen an entire crankcase filled with gasoline was when one of these vehicles came into the shop, and it had this style system on it. Oh boy, I'm losing it here. It had this style system on it. Okay, clear. It had this style injection system on it, and what happened is the customer shut the car off and all of the fuel every time they were shutting it off was just running out one of those injector nozzles. So like the little check valve was broke, and this injector was holding fuel pressure from the tank, and every time it shut off, it was dumping all that fuel. And it may have been a combination between that and the actual lines cracked. And so that's the other way these things fail, is the lines would snap on them, and fuel pressure would literally just go straight into the crankcase, because these are located underneath the intake manifold. And so as you had the fuel pump on, it would just be spraying fuel straight into that unit. And if the unit was cracked, it would dump fuel right into the crankcase. And if it wasn't that the unit was cracked or the line was cracked, it would dump fuel straight out that injector nozzle right into the cylinder, and it would fill up the entire cylinder with fuel. And so they would hydrolock. So the customer would drive the car, they'd get to the gas station or wherever they were going, the grocery store, they shut the car off, and as they walk away, all the fuel pressure is bleeding off through one of those poppet valves and dumping right into the cylinder. So when they come back out, they go to crank it, they get a no start and a no crank. Even they just hear a whine sound coming from the uh, the starter, because the engine's trying to compress the fuel that's sitting in that cylinder. And in extreme cases, if the entire body of this thing snapped, it would just dump all that fuel right into the crankcase. And the first time I saw that, it was a eye-opening experience, seeing like 3 gallons of fuel come out of the crankcase. Of course, it was mixed with oil, but it's not a sight you ever want to see. Didn't necessarily cause permanent damage when that happened, but it's not good for the not good for the customer by any means. Okay, so we're getting to the end of the chapter here. I believe into idle air speed control motors. This is basically the last thing we need to discuss in the chapter. So bear with me for a few more minutes here. We'll get this wrapped up. So idle speed control is critically important for all engines, because we have idle at idle, we have a variety of loads that can be exhibited on the engine. So take, for example, you have a vehicle that's sitting at a red light. So you got your foot off the gas, your foot's on the brake, and you decide you're going to turn on the air conditioner. So you have an engine that's sitting at maybe 800 RPM in idle, and you hit the button, and you turn on the air conditioner. What what that air conditioner is going to do is cause additional load on that engine. And the AC pump requires a fair amount of horsepower, and your smaller engines, especially like your tiny little 4 cylinders, they need this system more than anything, because they have to have some way to bump up the airflow into that engine in order to keep the engine from stalling out. So another example is you're trying to parallel park. So you're on the street trying to parallel park while you're turning your tires, and you're not rolling. You're actually causing a lot of drag, friction between the bottom of the tire and like the asphalt. And so the power steering pump has to be able to move those tires. And so the power steering pump is going to ask the engine, it's going to demand some horsepower in order to spin that pump. And the engine will have a tendency to be pulled down in speed. So idle speed control systems have like an anti-stall theory in how they work. Like one of their purposes is to make sure the engine doesn't drop too low in RPM. And excuse me. And the other side of that is uh, like on a cold engine, allowing that engine to idle up in speed a little bit in order to get everything nice and warm, so our catalytic converter is able to warm up and be efficient, and so our cylinder heads are able to warm up and be efficient. You see this in the morning time. You start your car in the winter and it idles at 1200 RPM instead of 800 RPM. So the component that's actually doing that on your non-electronic throttle plate. That's important. Your electronic throttle plates are computer controlled, right? Drive by wire. Everything that was a cable actually leaving your pedal going to the throttle plate, if it has a cable and you're pushing on a pedal and you're pulling on a cable, you are controlling the throttle plate. The computer is not controlling the throttle plate. The only way the computer can elevate the airflow and increase the RPM of that engine is by incorporating some sort of bypass mechanism. So this illustration is showing you a bypass of the throttle plate. So as the computer determines, like, hey, I need to increase airflow so I can spray a little more fuel, so I can build a little more horsepower, so this engine doesn't stall as we're trying to parallel park, it will increase the airflow by bypassing the throttle plate via some sort of idle air control circuitry. There are a variety of systems on the market. This is a stepper motor style idle air control. It'll literally turn this pintle. There's this stepper motor will turn, I'm calling this part the pintle here, right? So it'll increase, so it'll stepper motor it one direction to push it and block off, and it'll also reverse polarity to that motor and cause it to open up. And so it'll allow, these ports are always here. So this port is always here. This port is always here. The only time air can flow is when the stepper motor backs off and allows air to flow. One of the issues with this system is the stepper motor itself. So if the stepper motor fails, you can end up with a car that does one of two things, or it could be a variety of things in between. Let's say hypothetically, it opens all the way up and then never shuts. So either electronically it fails, mechanically it fails, carbon builds up in these circuits, maybe it sticks in the high idle position. This is a scenario where you can have a car that wants to drive at 40 miles an hour without your foot on the gas at all. Customers might complain of you shifted into park, from park into drive, it bangs. Pay attention to the engine RPM. Most customers aren't going to pay attention to the engines running at 1600 RPM. They might complain that it's running a little bit loud, okay? But if that stepper motor sticks open, it's going to allow that engine RPM to rise excessively high if there's no additional load. So if it doesn't need the stepper motor at that position, because you're not trying to turn the tires in a parallel parking situation where you're not, hitting the AC switch on. If it doesn't need all that extra air, the engine will simply just run at a higher RPM. The other issue with them is if they stay stuck. So mechanically, electrically, if they don't ever open off their seat. Now you have a case where the computer is going to command idle air control to bump up the engine RPM, but it doesn't move. Therefore, you don't get any of that extra air. And now you have a case where the engine will stall. So this can go two different ways. If it fails in the open position, the vehicle can literally just run away. It won't go like 80, 90 miles an hour. It's not like a full throttle scenario. You're talking maybe 2,000 RPM in a max case scenario. It can only bypass so much airflow. But so in one case, the engine will idle high. The other side, it'll idle too low and stall. On your OBD2 cars, this system came out like in OBD1. This actually was technically, there were variations of idle speed control on your computer controlled carburetors, which were like the very, very beginning dinosaurs. They were not even computer controlled. They were literally just like a temp sensor, and it allowed positive power to hit this thing in order to like kick the throttle up a little bit until the engine warmed up to help with like carburation cars. So in OBD2 though, 1996, we started monitoring these circuits and watching RPM of engine speed. And so you started getting trouble codes for idle speed control faults, and it would point you to some sort of circuit, issue like idle air control. One of the ways you can try to diagnose these is with bidirectional controls. So in your scan tool, you can go into bidirectional controls and you can take control of your idle speed control motor. So you can actually try to run the RPM up and run the RPM down. And one of the things you can do while in bidirectional controls is cycle that idle air control motor 3 or 4 times in an attempt to break up maybe carbon that is stuck inside of it. So anyway, idle speed control motors have disappeared. They're gone in modern cars. Uh, Ever since the electronic throttle took over, there's really no need for an idle air control motor anymore. What the manufacturers are doing at this point is when you push on a gas pedal, you're pushing on a switch, just like your Xbox controller, and you're asking the engine to rev up. You're not pulling on a cable and mechanically opening the throttle plate any longer. And so now, since you have a computer controlling an electric motor on the entire throttle plate, if the computer decides that it needs more air, it's just going to open that throttle plate and let more air come in. It doesn't need a bypass circuit any longer. Make sense? All right, so I'm going to go ahead and end that here for the chapter. If you have any questions, concerns, comments, go ahead and get a hold of me. And hope you like this new way of doing it. I don't know. We'll see how well it actually comes out. But, all right, take care.